Okay, so in the last class we talked about various robot architectures. So robot architecture basically comes from the type of joint and the way the joints are arranged. And we saw that the first 3 degrees of freedom of the robot is used for positioning the wrist, and these positioning joints decide the architecture of the robot. So we look at the way in which the first 3 joints can be arranged, or the type of joints and the way it can be arranged. You'll be able to get different configurations, different architectures for the robots, and we found that there can be 5 commonly used body arm architecture, and they are basically the polar coordinates, cylindrical body and arm, Cartesian coordinates, jointed arm, and selective compliance assembly robot arm. So these are the 5 commonly used architectures, and we saw that this can actually be obtained by having 2 rotary joints and 1 prismatic joints, and then we can have the cylindrical body by having R, P and P. So 2 prismatic joints and then 1 rotary joint will give you a cylindrical body arm architecture. And then if you have all of them are P, you will be getting a Cartesian coordinate body and arm assembly. So this was what we saw in the last class. And again, the jointed body arm architecture is RRR. So if you have all the joints, rotary joints, then we will get it as a jointed arm body and assembly architecture. And another variation of this is basically a SCARA, again 3 rotary joints, sorry, 2 rotary joints and 1 prismatic joint. I will discuss it later. So you can get a different configuration known as selective compliance assembly robot arm. So we will look at these configurations and then look at their coordinate, sorry, the workspace, and then a little bit on the how the kinematics is, whether the kinematics is easy, simple or difficult, or why it is difficult, or why some configurations are preferred over the other by looking at these architectures. So first let us look at the polar coordinate body arm assembly. So as we mentioned, it's a R, R and P. So you have a P which actually goes, suppose this is the base, and if you have a coordinate frame like this, then you have 1 joint which is the prismatic one, which actually goes in this direction, and then we can actually have 1 axis which actually rotates with respect to this, that is, it can actually go, suppose this is the one, then it can actually go up and down in this direction, and then you can have go like this also. So basically it is going like this and then in and out. So you can actually get R and theta or R and phi like this, and then if you rotate this with respect to the vertical axis, you will be able to cover the 3-dimensional space. So the first one will give you to the planar positioning, this motion and this rotation will give you the planar positioning within a plane, and the out of plane motion is possible because of the rotation with respect to the base. So this is the way how this RRP is arranged, and the structure will look like this. So you have this motion, the prismatic joint going out of this or going inside, so you can actually get a motion like this, and then the rotation about this axis, the horizontal axis. So you have a vertical axis rotation and a horizontal axis rotation. So the horizontal axis rotation gives you a planar motion with this, and a vertical axis rotation gives you the out of plane motion also. So this way you will be able to get a 3-dimensional workspace in polar coordinates. So r theta will be the positioning that you can use, and then phi will actually give you the y dimension also. I mean xyz coordinates can be obtained by these 3 joints. So if this is the wrist point, so assume this as the wrist point, then we can see that the wrist point can actually be placed in a 3-dimensional space using the R, R and P configuration. So that is basically the polar coordinate body and arm assembly. Not a very popular configuration, but for a very specific application you may find this as useful. We will look at that. Okay, now the workspace, or we call it as the work envelope of the robot, because workspace has got a little bit more specific meaning. Work envelope is the maximum envelope that the robot can actually reach. That is basically known as the work envelope. So the gross work envelope of a robot is defined as the locus of points in three-dimensional space that can be reached by the wrist. So the points where the wrist can reach in three-dimensional space is generally known as the work envelope. Sometimes work envelope and workspace are used in the same context, but in general, work envelope is the maximum that you can reach overall in the three-dimensional space. Workspace may be a subset of the overall work envelope. Because that depends on the joint limits and other things. So without considering those joint limits, you can say this is the gross work envelope. We can think of a robot. And this work envelope is basically depending on the positioning axis only, because we are talking about the wrist, and the wrist positioning is decided by the major axis, and therefore work envelope is decided by the major axis. I mean the type of joints in the axis, type of joints available, and the orientation or the way in which the joints are organized. Okay, so it shows the polar workspace that you can actually achieve this kind of robots. Now, if you look at this is one of the commercial robot which actually uses a polar workspace. So you can see that all the motors will be somewhere at the base, and even for this linear motion also the motor will be somewhere here, and this can actually reach the base also. The end can actually reach the base and then pick up something and then do some task. So that is why that is one of the advantages of these robots. And since all the motors are somewhere at the base, you can actually have large payload also, because these motors need not carry the load of other joints. So this is one example for a polar workspace robot. Not very popular. Not you don't see them many in the industry. So these are the three parameters that actually defines the motion of the robots. So you have a linear motion, you have two rotations, theta and phi. So the x, y, z, the position that the wrist can reach is a function of these three parameters, theta, phi and rho. So this is the relationship that you can get from with the Cartesian coordinates and the joint parameters. So we call this as the joint parameters, because these are the variables that actually changes the position of the wrist. And this relationship is not very straightforward compared to other robots. So that's why we call it as a little bit of complex kinematics, because you cannot directly tell what will be the XYZ position by when you change any one of these. You need to have a proper kinematic model for that one. And other things like large reach from the central supports, bend to reach objects on the floor, and motors 1 and 2 are very close to the base, so it can actually be positioned in a proper way. You don't get too much of mechanical design issues with this kind of robots. So that's about the polar coordinate robots. Now, if we so this was basically RRP. Now, if you change this to RPP, that is two prismatic joints and one rotary joint, then you will be getting this this as a cylindrical coordinate or cylindrical body and arm robot, or a cylindrical coordinate robot, or cylindrical body and arm assembly robot. So it consists of a vertical column and a horizontal motion. So you can actually have this kind of motion and this kind of a motion. So you have the arm which can be moved out, in and out, and vertical column relative to which an arm assembly is moved up or down. So you can have up and down motion and then in and out motion using this, and then you can have a rotation with respect to this axis also. So these two P will decide the motion in this plane, and the rotation will decide how it goes out of the plane also. So that is the way how this cylindrical body arm assembly is organized. So you have one rotary joint and two prismatic joints. So this prismatic joint will take you in this axis. Suppose this is the X and Z axis. So the x plane motion is decided by these two, and the y coordinate will be decided by the rotation with respect to this axis. So this is the cylindrical coordinate. So as the name suggests, the workspace is cylindrical, but of course because of the mechanical requirements, you won't be able to get the complete cylinder as a workspace. The workspace will be having a concentric to concentric cylinders, and in between the space will be the workspace of cylindrical body arm robots. So can you draw the work envelope for this? What will be the work envelope for these robots? So this is a typical cylindrical robots in industry, what you can see. So the workspace will be like a cylinder. So you will be having a cylindrical workspace, outer envelope, and then there will be an inner envelope. Because of the mechanical construction, you need to have joint, so you cannot reach the center. So it will be like this. And this area will be the workspace that you can, or the envelope that you can have. And because of this space, it is known as a cylindrical robot. Okay, so this will be the workspace that you can see. So you will be having this here and then here, because this distance is decided by the this motion. So what is the range that you can have that decides this, and this height is decided by the motion that you can have in this axis. So these two are decided by these two prismatic joints, and then assuming that it can go all the way 360 degrees, you will assume that this one. But not all the robots will be able to go 360 degrees. There will be joint limitation. So the actual workspace will be a subset of this again. So what are the parameters that will decide the XYZ here? A function of two linear motions, right? So we call it as rho and z, and then an angle with respect to this. So these three parameters will decide the position of the wrist. Again, not a straightforward relationship. These two can be decided directly. Compared to the previous one, this is simple because the x position and z position can be easily obtained by these two joints. So depending on how much this has moved, you will be able to get this, and then the angle will be decided by this one. So y will be decided by the rotation, and s, x and z can be easily obtained like this. So that is the way how it is defined. So this is an example for a cylindrical workspace robot. So you have three parameters, theta, z and rho, and kinematic model is simple compared to the previous one. And of course, when you are using hydraulic actuators, you will be able to get large forces because it's all vertical and horizontal motions. And work volume is a bit restricted, requires guides for protection, because the linear joints are always troublesome in especially in a industry environment. May get corroded or get damaged easily, because you can see there will be protection on this surface. So these are all provided with bellows to protect the slides from getting jammed due to some environmental pollutants or something like that. And they should be very smooth always, otherwise you will get a lot of motion difficulties. So that is one of the difficulties with the prismatic joints. So you need to have proper protection for them, otherwise it will get damaged. Okay, the next one is basically the Cartesian coordinate, called as P, P and P. So this is the Cartesian robots. All the joints are prismatic. So you can see there is a motion like this, a motion like this, and a motion like this. So all the coordinates X, Y and Z directly related to the movement of these robots. So it is very easy to find out the position of the wrist. Suppose this is the wrist. We can easily find out the wrist by looking at the motion of each joint. So it's a very simple kinematic model, and exactly, and actually there is not much of modeling here. The position of X is decided by one joint, Y is decided by another joint, that is decided by the other joint, and therefore we can very easily find out the position of the tool race. So it's a very simple kinematic model. So this is one example for a industrial robot with all the three prismatic joints up to the positioning, up to the wrist. Any questions? Chinmay, you have some questions? Okay. Yeah. So as you can see, it is a very simple design, because most of we use this kind of things very well. Most of our XYZ tables you use in many of the equipment where you want to position it in the three-dimensional space. Go for this kind of mechanical configuration. So one advantage is that it is very easy to visualize and control. So control becomes very easy because you don't need to have any kinematic model, just control individual motors for whatever position you need. The one disadvantage is that, as in the previous case, all these need to be protected, all the slides need to be protected, otherwise it will actually get jammed or it will start malfunctioning. It won't be able to move because of some kind of pollutants or other debris getting into these slides. Another disadvantage, okay, what will be another disadvantage of this one? Can you tell me? Workspace is discontinuous. Why? Okay. Okay, we'll see workspace later, but any other thing? Load, okay, yeah, load will be an issue because if you have large reach, then you need to have bigger very load carrying, then this motor will be of larger weight, it has to be held by this and it has to be held by this. That may be one reason. Okay. Another major problem with this is that the actual workspace available or the work envelope available will be something like this. Sorry. But the total robot size will be much bigger than the size of the workspace that you can get, because each one has to move. So you need to have a very large size of the robot to get a smaller workspace, or if you increase the workspace, then the robot size also keeps on increasing. So it is not, it's unlike other configurations. This one has got the largest size of the robot for a given workspace. So that is one disadvantage. So it's not commonly accepted unless you have a large space available. And if you have seen some Cartesian robot, the robot will be very big and the workspace will be somewhere in the center, a small area. If you can afford to that kind of thing, and you don't, yeah. Yeah, that is what I'm, even in that case, the workspace available will be very small compared to the size of the robot. So that is the way how normally people make. So they will be making a structure like this, and then you will be having the slides on this, one slide here and another slide here, and then one up and down. So the workspace will be somewhere in the center. You will be able to get a workspace here, and not a full workspace you will be able to get. So the overall size of the robot increases when you go for all prismatic joints. So that is why this is not preferred normally, most of the industrial robots won't go for this kind of a configuration unless there is a specific requirement which warrants the use of this kind of construction. So that is the jointed, the prismatic joint, prismatic robots. So this is a Cartesian workspace robot or a prismatic robots. So the workspace is Cartesian, and you can actually find out the workspace will be something like this, and of course there may be, depending on the construction, you will be having the workspace will be within this, and you can actually get XYZ position depending on the stroke length that is available for the robot. So depending on where actually you place the workspace, you will be able to get a variation of this as the workspace or the work envelope of the robots. So XYZ, so directly, so you don't need to have any other parameters here. So the linear motions XYZ depends on that is actually the position of the wrist itself. So you don't have any particular relationship here. So simple kinematic model, rigid structure, and then robots require large working volume. The working volume is smaller than the robot volume, requires free area between the robot and the object to manipulate, guides protection. So all those things are the disadvantages. Advantages are it is very easy to visualize and then program. So that is the advantage. All right. So the next one is the jointed arm architecture, which is the most commonly used architecture, where we have all joints as rotary joints. So this is the wrist point. If this is the wrist point, okay. This case, no, sorry. This is the wrist points. These are the wrist joints. So this is the wrist point. So you have one rotation here, and the rotation here, and then the rotation here. And so you have three rotations, three rotary joints. So the first two rotary joints, so these two rotary joints, these two rotary joints will decide about this plane motion. Within this plane, it will decide, and this one will decide out of the plane. So if this is the X, Z plane, so then XZ is decided by these two joints, R3 and R2. The positioning within this plane is decided by this, and then out of this plane, the Y coordinate is decided by this rotation. So this is the way how the robot joints are placed. So you'll be able to get all the XYZ coordinates within the work envelope. And most of the industrial robots follow this kind of a configuration, the first three joints. So depending on the robot, this can actually, the axis may be different. Instead of this rotation, it can have a rotation here itself, and then have this axis, rotational axis can be different orientations. But the first three will be rotary joints, so that you will be able to position the wrist in XYZ plane. So that is the jointed arm architecture. So there are many names: jointed arm, anthropomorphic arm, and etc. etc. But this is the configuration that human also has got three joints, though we don't have the axis separated like this. So we can actually use these three joints to position the wrist in any plane. So I want to plane this plane, or I want to move to this plane. I will be able to use these three joints here to place my wrist in any coordinate in the XY three-dimensional space. So the same configuration is used in the industrial robot also. So this is the general architecture. So rotational axis, and rotational axis. So three rotary joints. So what will be the workspace? Pardon? Work envelope will intersect the robots. Okay, what do you mean by that? Okay, so you can see this one actually can go up like this, right? The first two joints can actually take a path like this, but then when the two joints are in this position, so if you take these two, then only this can actually move, or this has got its limit, then it can actually move like this, and then this can also move like this. So you will be getting a a complex work envelope, not exactly like a circular path here, or an arc you cannot get, but it will be something like a complex one, and then similarly you will be getting a complex arc path like this. So it need not be something different from the previous configurations. You cannot define the exact shape, but it will be a slightly complex work envelope you will be able to get. So you can see here, so tap to here, and then it actually changes its configuration and then comes like this. Okay, the exact shape depends on again the limits and the mechanical structure it has, but in general you can say the work envelope will be in this region. Not all will be available for all the robots. Most of the robots will be having a workspace in this area more, and then backside it will be having a very limited work envelope. I'll show you a typical work envelope of an industrial robot, but this is the general shape that you can see for the RRR robots. So you will be able to see this kind of robots. We have in our lab also, we have few robots with this kind of architecture. So this shows the typical work envelope of not the typical one, but for a particular robots with the dimensions. You can see this will become the actual workspace that the wrist can reach, because as it comes up here, then it has reached one range of this joint, then the next range will start here, then the next one like this. You will be able to see a work envelope which can actually reach. Now, most of the robots will be designed in such a way that they have the large workspace in the forward region, so that it can actually do the operation. So behind not many operations will be carried out, and therefore this workspace will be somewhere like this only. Again, depending on the range that you decide, you will see that it can actually be less or more, but most of the time the workspace will be in this region, so that it can carry out some task. Again, there may be pockets where it cannot reach because of the joint limits. So the reachable workspace may be again less, but this region, every robot designer will try to make this region very accessible and without much of non-accessible areas. So as long as you can get a good workspace over this region, then the robot design is considered to be the good one for a particular application. So though it can reach here, not always this workspace will be used for any practical purpose except for some moving of some objects and all. We will see how we can identify the workspace of a robot later. So once we know these joint limits and the relationship between these coordinates, suppose we know the relationship between the coordinates and the joints. So we have three joints, so theta, phi and psi. So I put this as three joint angles. So if we know this relationship between the coordinates x, y, z and then the joint angles or the joint variables, then we will be able to find out for every value of theta and every value of phi and every value of psi, you will be able to find out what is the position that it can reach. And the set of all these points basically makes the workspace. So the workspace points, all the points in the workspace can be obtained by substituting the value of theta, phi and psi in this relationship, and you will be able to get all the workspace. So once we develop this relationship, then we can actually write a simple program looking at the minimum and maximum limit of theta, phi and psi. You will be able to find out all the points in 3D space where the robot can reach. That is the reachable workspace that we have. Workspace. Oh, sorry, in this case it is mentioned as center effector. No, this is for the wrist. P. Symmetrical with respect to this, you are telling? No. So the reason is that this joint, suppose you take this joint, you can actually come up to here. I mean, can have a limit up to like this, but here it is having a limit only up to here. So this may be the joint limits that will be set for this joint. Oh no, this will be actually like a rotation, how much you can rotate with respect to this axis. That is with respect to the vertical axis. Now this can actually be rotated, that will be the volume. Okay, so this is in this plane only. Okay, this is shown in this plane, let's say this is xz plane. Now how much it can get in y depends on how much you can rotate with respect to this axis. So the whole thing, this workspace, this workspace can actually be rotated. You can sweep through this angle, that will give you the volume. So this is the area that you can get in one plane, and then you sweep this. And again, it need not be 360 degree, there will be a limit for this. There actually it will stop. Okay. All right, so these are the most popular configurations, and it's a bit complex kinematic model. So it's very difficult for you to predict what will be the XYZ position just by knowing the theta. You need to calculate because it's not a direct relationship. And that is basically the kinematic model we talk. So how the position of the tip is related to the joint angles. We need to develop a relationship for that. And it can get the large working volume with respect to the robot size. For the given robot size, the largest work volume can be obtained for the angular robot configuration, and the least is for the prismatic configuration. And it can reach the upper and lower side of an object, that I will tell you later. So the complex kinematic model. So linear movements are difficult. When I say difficult, suppose you want to get a motion in like this. Suppose I want the tip to move from this point to this point. I need to control all the three joints. Okay, in this the planar motion, but in the three-dimensional space you want to get a straight line. You need to control all the three joints and then move the robot to get the straight line motion. So compared to other robot configuration, this is slightly complex to get a linear motion. It is possible, but maybe a bit complex to get a straight line motion because all the three joints need to be controlled. Okay, let me finish this also. So SCARA is basically a RRP robot. So you have two rotary joints. So two rotary joints and a prismatic joint. So this is the configuration of SCARA. It stands for Selective Compliance Assembly Robot Arm. It's a very commonly used robot because a lot of pick and place operations requires a bit of compliance in one direction. That is, it should be able to move it in a particular plane so that you can get compliance and then insert some, if you have like a peg and hold assembly problem. So you will be able to get in compliance using this kind of robots. So the peculiar design feature here is that all the axes are vertical. So you can see all the joints are in vertical direction. All the axes of rotation are in vertical direction. There are no other joint axis. Everything is in vertical direction, and therefore it provides compliance in the other direction, other plane. So that is the advantage of this. Except that vertical axes are used for shoulder and elbow joints to compliant. So just to be compliant in horizontal direction for vertical insertion task. So you are getting a compliance in the horizontal direction because all the joints are in vertical, and that is the advantage of going for this configuration of robots. Other than that, it is like an RRP robot, normal RRP robot. The only difference is that all the axes are in vertical direction. Again, since these are the vertical direction, the inertia of this arm is not actually reflected onto this because it is moving this direction. The load is actually in the vertical direction, so it's not reflected on these axes. That is another advantage of this. Apart from the compliance, actually this motor need not take the load of these motors. So because it's vertically mounted. And the workspace will be something like this. It is almost like a cylindrical one, except that you will be having some kind of a, so depending on this, because of this joint, you will be having a small curve over here when it comes to the end of the work envelope. Other than that, it will be more like a cylindrical workspace. Yeah. Pardon? Advantage. So basically, you have this vertical load here. I mean, the motors are here in the vertical direction. This is also vertical direction. So this load is not reflected on this motor because this motor is actually moving in this direction. So the vertical load is not actually reflected onto this motor. Compared to the other kind of robot, this load will be reflected onto this when you have to move like this, right? So in this case, it is not reflected as an inertia. So these are some of the typical robots that you can see. This was a video, it's not working, but you can actually get a lot of examples from the literature. There are a lot of such robots available in the market, and we also have one robot. We'll show you we'll demonstrate this robot to you next class, one of the classes. So, sorry, there's something wrong here. Don't take this. Okay, here theta 1, theta 2, and D. Okay, so it's a P. So it's by mistake it is given. I'll correct it. It's not rotation. No, see, what I'm saying is that the gravity load will not be acting on it. Only the acceleration load will be coming. So if you want to accelerate it, you'll be having a load, but the weight of the motor will not reflect onto this because that is taken by the structure itself. That will be taken by the structure. So you design the structure in such a way that it can take the load. So the motor need not take the gravitational load of the other motors. That's what I am saying. So it can have very high speed. So very high speed assembly robots are made using this kind of an architecture. And you have only vertical axis. Okay, so we'll stop here, and we'll just talk briefly about the wrist configurations also, how the wrist can be assembled, and then we move to the kinematic relationship in the next class. Thank you.